So last time we talked about the mirror descent method. Right. So this is the main idea. At xt in every iteration we build an approximation model for the function. What we do is that so this is like a first order Taylor expansion plus a divergence term. Okay. This is a constant, this is a linear function in X, linear approximation, and then this is a divergence term that controls the step size between X and XT. Okay. And this is a Bregman divergence. And we have shown that, like in this table, if you pick different phi functions, then the Bregman divergence can reduce to different distance or divergence metrics. Okay, the most frequently used ones are the first one, the Euclidean distance. Second one is entropy or KR divergence. This is frequently used, very useful in the mirror descent method. And the key question for mirror descent algorithms, like we need to, for a specific problem, we need to pick a proper phi. We need to pick a proper divergence function that fits into the geometry. And later on, we will show some examples to illustrate this idea. But now let's continue the discussion on Bregman divergence. Okay. So this divergence shares some similar properties with the distance function. For example, it is non-negative. For any 2 point X and Z, it is non-negative because if you look at the definition of Bregman divergence, this is guaranteed to be non-negative because phi is a convex function. By convexity, this phi x is bigger than or equal to phi z plus this inner product, simply by convexity. Therefore, this is guaranteed to be this divergence is always non-negative and equals to 0 if and only if x equals to z. So it looks like a distance. And moreover, if phi, suppose phi is a mu strongly convex function, then such a divergence can be lower bounded by the Euclidean distance. For example, in the previous table, in the first example, this phi is 1 strongly convex. And therefore, this distance is lower bounded by the Euclidean distance. In this case, it is actually equal to this distance. But in general, if phi is mu strongly convex, then this is lower bounded by mu over 2, the distance, the Euclidean distance between these two variables. So this also shows that they are kind of similar. And lack of symmetry, d phi xz, in general, it may not equal to d phi zx in general. For example, if you look at the second, the Shannon entropy example, phi equals to Shannon entropy, and then d phi x and y is given by the it's given as the KL divergence. This divergence is asymmetric. If you switch x and y, it is not equivalent because of this log. Okay. So this is a not asymmetric case. But for the first example, it is symmetric. You can switch x and y. Okay. But in general, this divergence may not be may not be symmetric. So these are some properties. And also we have this linearity property. If we define the divergence based on a linear combination of two phi functions, phi1 plus lambda times phi2, so it's a linear combination of two, then we can simply, you can follow the definition and check that this can be decomposed in a very natural way. So it's simply the divergence based on phi1 plus lambda times the divergence based on phi2. So it is linear with regard to this phi function. And also you can also check the gradient. If you take the gradient of this divergence with regard to the first variable, then it is essentially the difference of the gradient of this phi function at x and z. Again, this can be seen from this definition. You take gradient with regard to x, this becomes gradient phi x. This goes away because it's a constant. And this one, you take gradient with regard to x, you only have this gradient term, right? So you end up with gradient of phi x minus gradient of phi z. So this shows that the gradient of this divergence with regard to x is basically the difference of the gradient of phi. Okay. And moreover, we have this 3-point lemma. For every 3 points, x and y, z, x, y, and z, this equality holds. Right? The divergence between x and z can be is equal to divergence between x and y and z minus this inner product term. Okay. So this gives a relation among the divergence or the distance amongst multiple points. In fact, if we choose phi to be the square distance, Euclidean square distance, and then this d phi xz will simply become the Euclidean distance between x and z. And then this formula simply reduces to the law of cosine. X, Y, Z, 3 points in the Euclidean space, their distance satisfy this cosine law. And this is simply a generalization using the Bregman divergence. And to verify that, you simply plug in the definition of Bregman divergence. You can check these two sides and they are equal. So you can see in general, such a equality holds for highly nonlinear divergences, right? So in the Euclidean case, we are familiar with this law of cosine, but this is kind of a Euclidean geometry where everything is kind of flat. But this can also generalize to highly nonlinear spaces, highly non-Euclidean spaces. And this is the proof. I won't go over that. Simply plug in the definition of Bregman divergence. You can verify that. And we can also define the projection operator based on such Bregman divergence. Okay. So we want to project x onto a set C. Okay. Again, we project x onto set C, but now the projection is based on a Bregman divergence. So the definition is very natural. I'm looking for, now this is a fixed point X. I look for the point Z within the set C so that it has the minimum Bregman divergence to X. So it follows the same definition as the Euclidean projection. So we denote this as projection of X onto C, but under this Bregman divergence. So Bregman's divergence is denoted by this phi function. Yeah. And again, this is a generalized Pythagorean theorem. The right-hand side is the Euclidean case, and left-hand side is the Bregman divergence case. Okay, so what this theorem says is that if you project X onto set C based on a Bregman divergence, right? So X, you project this point onto this set C under this Bregman divergence, and this XC phi denotes the projection point. Okay, so this is a projected point. Then for any other Z in this set, we have the following inequality. So the divergence between Z and X, this one is bigger than or equal to the divergence between Z and the X, the projection point, plus the divergence between X and the projection point. In the Euclidean case, right, if you project a point onto a set C, imagine this is a hyperplane. You project a point onto a hyperplane, then you know that this line in this triangle, this line would be, the distance of this line would be bigger than the sum of these two. This is sort of the it's not triangle inequality, so it's a different thing. Okay, so we have this generalized theorem. In fact, if the set C is a affine plane, then this inequality becomes equality. And this is a proof for this theorem. We can quickly go over the proof. So first of all, by the gradient formula, we know that gradient of Bregman divergence with regard to the first variable Z is simply the difference of this gradient. Okay, but now I'm specifying this Z to be the projection point. So Z equals to this projection point. And therefore here, Z is also replaced by this projection point. Okay, this is just the gradient formula for the Bregman divergence. And because this point is the projection point, right? That point is the projection of X onto C under the Bregman divergence. And this this is a constrained convex optimization problem, because the objective function, if we view this problem as an optimization over Z, first of all, this function is convex in Z because it's a Brakman divergence. So it's convex in Z. And it is a constrained problem because Z is constrained to be within set C. Right? So it's a convex optimization, constrained convex optimization problem. And then we can utilize the optimality condition for constrained convex optimization. Basically, the minimizers, this minimizer must satisfy this optimality condition. Okay, so for n in Z in this set C, this inequality must hold. Well, this G is from that is the gradient of this objective function. Okay. So there's a reference, but I won't go into the detail. Basically, for n in convex constraint problems, this is similar to gradient equals to 0, right? when there's no constraint. Okay. Then you plug in this into this G and this inequality and rearrange this inequality. So you basically get that 0 is greater than or equal to this inner product. And this inner product is about 3 points: X, the projection point, and Z. And again, you can check that this equals to these 3 Brakman divergence. It is an exact equality. And then this will prove the desired result. So this is this theorem. And these are very useful when we analyze the mirror descent algorithm, because it involves this Brakman divergence. Yeah. And actually, mirror descent was first developed in a very different form. Okay. So this is an alternative form for the mirror descent. So let's see if we can see this clearly. Okay, so first let's go to the mirror descent algorithm. This is mirror descent algorithm. This algorithm in this form, it is described by a optimizations problem. Xt plus 1 is defined as the minimizer of this constrained optimization problem. Yeah, but it can be shown that it is equivalent to the following 2 steps. Well, the first step is sort of similar to a gradient or subgradient descent step, except that instead of operating on yt plus 1 and xt directly, we operate on their gradients, corresponding gradients. Okay. imagine if we ignore this, if there's no such gradient operators, then yt plus 1 equals to xt minus this eta t times the subgradient. This would be a standard subgradient descent algorithm, right? But in mirror descent, we operate on the gradient space instead of the original vector space. So this update is performed on the gradient of phi instead of the variables directly. After that, we will do a projection. After that, xt plus 1 is simply projecting the obtained yt plus 1 onto the set C under this Brakman divergence. So it is a two-step process. One is a subgradient method, but in this gradient space, and then followed by a projection. We can actually combine these two steps in one line by, the first line is about yt plus 1, and then we can solve for yt plus 1 and plug it into the second line. Okay. And this will be combined into such a closed form. Well, this star means this phi star corresponds to the conjugate function of this phi. Okay. Phi star x is defined in such a way as the conjugate function. Okay. So this form is very hard to understand in an intuitive way. But when this algorithm was originally developed in the 1980s, this is the original form, which looks a little very complicated. But later on, people realized that later on people realized that that algorithm is actually equivalent to such an update rule, which is more intuitive because this is essentially tells us how we can simplify or decompose the optimization problem into a sequence of smaller problems. Well, each problem is a kind of a Taylor expansion approximation of the function, the local approximation, but we simply need to choose different divergence to control this control the step size in every iteration. So, but we will stick with this simpler form. And I will not talk about there are some slides on proving the equivalence, but I will not go over there because we haven't really talked about this conjugate function. So let's directly jump to the convergence analysis of the mirror descent algorithm. So this is the general setup. We're looking at the constraint convex optimization problem where the function is convex and the Lipschitz continuous. And this is the setup. This is the same setup as the subgradient descent method. Now, because we are using mirror descent, so we have that Brakman divergence. So for that phi function, we assume it is rho strongly convex with regard to a certain norm. And we also assume that because it's convex and Lipschitz continuous, so the subgradient of this function is bounded. Okay, it's bounded by a constant LF. Well, this norm is the dual norm of the norm that we used in the strongly convex case. Okay, so this is a pair of a primal dual norm. Phi is strongly convex with regard to a certain norm, and then this subgradient is bounded by the dual norm of the subgradient is bounded by the Lipschitz constant. For example, if you choose L2 in the first bullet, then the dual norm is basically L2 itself. Okay. If you do 1, here it should be infinity norm. We will see some examples. And this is the convergence result. It's similar to the subgradient method. So we are looking at the minimum function value achieved in the first t iterations compared with the optimal function value. Okay. And this gap is controlled by the right-hand side. Well, essentially, this term is a diameter term, so it should be a constant. And this part is basically a sum of the squares of the step size divided by sum of the step size. We have seen similar results in the subgradient method. In particular, if we choose such a step size, it's roughly 1 over square root of t, but also with this constant coefficient, 2 times rho times r. Well, the rho is that strongly convex parameter. This is the Lipschitz parameter. R is the diameter of this constraint set under the phi divergence. But actually, R is the distance between your initial point and any other the maximum distance between your initial point and those points from the constraint set. But given a fixed initialization point, this would be a fixed constant. So if we choose this step size, plug it into this bound, we will have this convergence rate. It's roughly log t over square root of t, but as t goes to infinity, log t is will be dominated by the denominator square root of t. So it is roughly 1 over square root of t. Okay. And these two are fixed parameters. So this also depends on the square root of this r. Okay. And this is the critical factor in the convergence rate. You see, the convergence rate, log t over square root of t, this only depends on the number of iterations. LF and rho, these are depends on the problem. Right? LF is the Lipschitz constant, rho is the strongly convex parameter. So the only parameter that may depends on the Brakman divergence is this R. This R evaluates the Brakman divergence between your initialization point and the constraint set. So if you choose different phi in this Brakman divergence, that may significantly affect the scale of this term. Right. For example, suppose the constraint is the probability simplex constraint, meaning that for the vector x, they have to be positive, they have to sum to 1. Okay. Suppose the constraint is the probability simplex. And suppose the initialization point we pick is a very simple uniform distribution. Okay. So you have n coordinates, every coordinate gets 1 over n probability. Okay. So apparently this point is within the constraint set. Now let's compare two choices of the Brakman divergence function. The first choice, we can simply choose a very standard Euclidean distance. So phi x is 1/2 square of the L2 norm, a very standard Euclidean choice. And this function, apparently it is one strongly convex with regard to the L2 norm. Okay, we have shown this before. You simply take the second order gradient, you simply get one. You get a identity matrix, and yeah, so it is one strongly convex. Okay, so this is rho. This indicates that rho parameter is one. And then we look at this. We look at this term. This is the capital R that. This is this capital R term. Okay, so let's look at this term. Is the writing down the Brakman divergence. Under this choice, the Brakman divergence is simply the Euclidean distance between x and this initialization point, and raise it to the power of 2. And here we are looking at the x in the simplex set that has the largest distance. Okay, so it's supremum over x. And you can check that this equals to this one. It's a simple calculation. You simply expand this square term. You will have x squared, that's the first term, right? And 1 over n squared. You calculate this this vector's L2 norm squared. You will see it equals to. Okay, maybe I can do it here. Right, so we just look at this square term. So it's x minus 1 over n L2 square. Okay. Well, x belongs to the simplex. And this 1 over n means that it's a constant vector where all the entries are 1 over n, right? That's right. So and we just expand it. Okay, a vector with all the entries has values 1 over n. What is the L2 norm? Well, it's simply, you can calculate that this is simply sum of every coordinate is 1 over n. So every coordinate raised it to the power of 2. How many do we have? We have n coordinates. Right, so this is just this term and the minus 2. So what is this? This is a inner product, so it's a sum over xi times 1 over n, well, I from 1 to n, right? Because again, this is a constant vector, 1 over n. So this becomes what? This is 1 over n squared, but we have n terms here, so this is 1 over n plus 1 over n minus 2. This is a constant. This is a constant 1 over n, so it's 2 over n. Now this summation, right here is the critical thing. X in the simplex set, so the summation must be 1. X is in the simplex, so summation must be 1. Right. So this gives plus 1 over n minus 2 over n. So this gives x squared minus 1 over n. Okay. So it is equals to that. It's tricky. You need to utilize the fact that x is constrained in the simplex. Okay. So you can simplify it. And then this one is less than or equal to 1/2. We can just drop this small negative term. So less than equal to 1/2. This one, okay. So we can drop this term. And for all the x vectors in the simplex, you can check that the norm, L2 norm, is bounded by 1. Okay. The maximum L2 norm is the extreme case where one coordinate has 1 or the other has 0. So you can check this is bounded by 1/2. So in the end, what we conclude that the maximum distance is bounded by 1/2. Right. And then you plug this into the convergence rate, you will end up with the following rate. So it depends on the Lipschitz constant of this function under the L2 norm, right? Because here we choose this L2. But we can also, in the second case, we can also choose a different phi function, which is the negative entropy. And we define phi to be this one. And it can be shown that this function is one strongly convex with regard to the L1 norm. Okay, not L2 norms, with regard to L1 norm. Then, again, we look at this capital R term. In this case, phi divergence becomes KL divergence because we choose the negative entropy. There's KL divergence between x and x0. Now you write it down. Write down the explicit form of this KL divergence. Here it is. This x0 is the uniform distribution, so we have 1/n here. Okay, so this is what you get. And now this part, sum of xi is simply 1. Okay. So what you have is simplify the terms, you get this one. You get this one. And this is always negative because every xi is positive and every xi is between 0 and 1. So this part is always negative. So this is less than or equal to log n. Less than or equal to log n. Okay. And then plug this bound back into the convergence rate result. The convergence rate becomes this one, square root of log n, and this is the convergence rate part. But now we depend, the Lipschitz constant becomes a constant evaluated under the L infinity norm. This is because the dual norm of L1 is L infinity. Okay, remember, well, in our setup, right, if phi is strongly convex with regard to one norm, then in the end, the Lipschitz constant is associated with the dual norm. The dual norm. Okay. So here we have the dual norm of the Lipschitz constant associated with the dual norm. And the dual norm is with regard to the L1 norm. And we know the infinity is the dual of L1. So this is about L infinity norm. Right. So you can, this is case 1. Case 1, we have this rate and it's about L2 norm, right? It's the this Lipschitz constant is defined as the bound for the L2 norm of the subgradients. And here is this Lipschitz constant is the bound for the infinity norm of the subgradients. Of course, we have an additional factor of square root of log n, but this is not very big. Okay. So roughly speaking, these two choices, the convergence rate obtained under these two choices is roughly under the L2 norm choice, it's the Lipschitz constant under L2 norm divided by square root of t. For the negative entropy choice, it's the Lipschitz constant under the L infinity norm divided by square root of t. So we just need to compare these two constant terms and see if there is a significant difference. And in fact, the L2 norm and L infinity norm, these two can be very different in the scale. This is an inequality that holds for any vector. Okay. So for any vector, the L2 norm is always bigger than the infinity norm. And it's always smaller than or equal to the square root of n times the infinity norm. Okay. So this would be our LF2, and these would be our LF infinity, right? They could be very similar when the vectors is concentrated in one very few coordinates. Imagine if only one coordinate is non-zero, all the other are zero, then L2 and L infinity, they are the same. Now, what is the other case? The other case would be consider this example. Well, you have an O1 vector. The infinity norm of this vector is just 1, right? That's the maximum entry. But the L2 norm of this vector is square root of n, because you have dimension n, right? So square root of n versus 1 is a huge difference. So that's why here we have the square root of n. And this inequality basically says that the ratio between infinity and L2 can be as big as as small as 1 over square root of n. Okay. So in the worst case, we have 1, which means this bound is the same as the Euclidean bound. But in the best case, we can have 1 over square root of n. Okay. So this will be much smaller than the Euclidean case by a factor of 1 over square root of n. Well, this n is the dimension of your problem. So if you're looking at a problem with thousands of tens of thousands dimension, this will make a big difference. Right. And these two differences, they are induced by the choice of the Bragman divergence, right? When we choose different phi functions, we are basically choosing different geometries. These different phi functions, they are corresponding to different types of geometries. So if we choose this Euclidean phi, we are considering this optimization problem under the Euclidean geometry. If we're choosing this entropy phi, we are consider the problem in a different geometry. And consequently, this will affect when we choose different phi, they will be strongly convex with regard to different norms. norms represent the underlying geometry that we are considering. And then the dual norm will also know. So in the end, the dual norm will determine the Lipschitz constants that we. So the dual norm is the geometry that we will use when calculating the Lipschitz constants. If you choose different phi's with different associated with different norms, then we are looking at different dual norms. So this will make a huge difference in the underlying geometry. Right. So this suggests that when we deal with optimization problems with such simplex constraints, right? It is better to use a mirror descent with the entropic phi function. This is the right geometry that to use for this type of constraint. Yeah, and this is an example of robust regression. We have seen this in the homework. We are doing least square regression, right? But we also have this difference term AIX minus BI, right? This is the variable optimization variable. AI is the measurement vector, BI is the observation. Okay. And this is the error. This error. So in our homework, we are looking at L2 error to the power of 2. That's the least square error. Here we are looking at it's like an L1 error. So we are looking at, for this error vector, the objective function is defined as the L1 norm of this error vector. So this is L1 norm. And this is called a robust regression because in statistics, this has been shown to be very robust to outliers. And here we have a constraint where X is restricted to be on the simplex. Okay, and this is how we generate data, very similar to what we have done in the homework. So I will skip this one. Basically, it's a L1 norm with a simplex constraint. And this is a comparison between those two choices of phi's that we just talked about. If you choose a Euclidean phi, that simply becomes projected gradient descent, projected subgradient descent. And it converges very slowly. The y-axis is in a log scale. Okay, so you see it converges very slowly. But if we choose a negative entropy phi, well, the geometry fits the underlying problem very well. Then you can see the algorithm can converge to a very high accuracy. So this shows that picking the right phi function in the Brakman divergence can make a huge difference. Yeah. Now we are going to prove this result. Okay, prove this convergence result. And this is a fundamental inequality to prove the main result. This inequality bounds the gap between xt and the optimal function value. And this gap is related to such a distance. okay, plus some residual terms. Okay. And these two divergence terms, they have very similar structure, but here's xt, here's xt plus 1. So later on we can do a telescoping and cancel out the intermediate terms. Okay. But first, let's prove this key inequality. So we start from the left-hand side, which is fxt minus the optimal function value. Okay, so we start from the left-hand side. And the first inequality, we simply use convexity. Okay. Well, gt is a subgradient at xt. So by convexity, right, f is convex. So we have this convex inequality by convexity. And then what is gt? gt is the subgradient. gt is a subgradient. So by the mirror descent update rule, gt equals to 1 over eta times the difference of the gradient terms. Okay, this is given by here. This is in the alternative form of mirror descent. Right, gt is given by the difference of these gradient terms. Okay, so basically this is the update of the algorithm. Algorithm update. Okay, now we have a very nice inner product structure. Gradient phi xt minus gradient phi yt plus 1 inner product with xt minus f star. Okay, and this is a very important structure for Brakman divergence, because such an inner product involves 3 different points: xt, yt plus 1, and x star. Right, 3 different points. It can be shown that this equals to the following 3 Brakman divergences. Okay, so these are 3 Brakman divergences. Each involves 2 points. Okay, it's not easy to see, but if you start from this line, plug in the Brakman divergence definition, you can get that one. Okay, it takes some calculations. So this is related to 3 Brakman divergence terms. Okay. Now the first 2 terms, we keep them. So these are the same. For the last term, we use the Pythagorean lemma that we just developed. So this divergence term is less than or equal to these 2. So let me highlight this part, right? So this divergence term less than or equal to the sum of, actually it's bigger than or equal to, because of the negative sign. So this is bigger than or equal to the sum of these 2 terms. And by utilizing this Pythagorean lemma. And here, notice that xt plus 1 is a projection of yt plus 1 onto the set C. Go back to this alternative form. Go back to this alternative form of mirror descent. Ft plus 1 is the projection of yt onto set C. That's why you can apply that Pythagorean lemma. Okay, so you decompose this one into sum of these 2. And then you just rearrange these 4 terms. Now you have 4 Bragdon divergence. Okay, rearrange them, and then you will have two difference terms. The first difference term is what we need. Right? We have xt, x star xt, and x star xt plus 1. And then we still need to handle the second difference term. Okay. And we can claim that the second difference term can be controlled by roughly the step size to the power of 2. Okay, we claim this can be done, and then we plug this one back into the previous inequality, we will get the desired result. Okay. So we just need to justify this line. Control this difference term in terms of constant, small constant. And intuitively, it makes sense because yt plus 1 is fixed. The only difference is xt and xt plus 1. So if the algorithm if the algorithm takes a very small step size, then these two divergence terms, they should be close to each other. Okay. Yeah, and so let's just compute these two difference terms. Okay, so you just plug in the definition of Bragdon divergence, you will get such a result. Okay, plug in the definition to these two divergence terms. And then I will keep the second, I will keep this inner product term. So this term is copied here, is the same, right? The first term is a difference of function values. So I will control this difference by strong convexity of phi. Okay, so by strong convexity. Okay. So it is rho strongly convex. So this inequality will hold. And then I rearrange these terms, put them together, I will get this one. Okay. After that, now by the mirror descent update rule, this difference of gradient terms is essentially the step size times the subgradient. This is just by the mirror descent update rule in their alternative form. And then we can bound this inner product by Cauchy-Schwarz inequality. So this inner product is less than equal to the norm of this difference term times the dual norm of GT. But the dual norm of GT is bounded by the Lipschitz constant. So I have that constant here. Okay. And then the last line is basically optimize this these two terms as a quadratic function. Okay. Basically, what you have is eta t LF times delta minus rho over 2 times delta square. Well, delta represents this norm. Okay. And of course, this delta is non-negative. So for such a quadratic function in the positive domain, you can show that it is bounded by such a constant. Okay, so you don't care about the specific value of this difference term. Just view it as a quadratic function on the positive domain. So you can show this is bounded by this term. So this proves that this difference term can be controlled by. It actually fits our intuition, because the difference term is upper bounded by the step size to the power of 2, which means if you take a very small step size, these two differences will be very small, right? And that is intuitive, because if you use a very small step size, xt plus 1 will be very close to xt. So they will look very similar. Okay. So then this will complete the proof of 5.4. So now we have proved this lemma. We have this result, and then we simply need to utilize this lemma to prove the convergence result. So what we do is telescope this lemma over T, so that these two the difference term can cancel out. Okay. So this is lemma 5.4 copied here, and we just sum over K from 0 to T. Okay, so the left-hand side summation, right-hand side, once you sum them up, intermediate term cancels, so you only have first and the last term. This one, you sum them up. Now, this is a negative term, you can drop it, because this is less than or equal to. So this is this term can be bounded by this supremum. Okay. And then I copy this term here. Now for the left-hand side, this summation is, I can lower bound this term by the minimum function value among the first two iterations. And then I can take this as a common factor. So I can divide this to the right-hand side. Okay, so in the end, we can prove the convergence rate result. Yeah, so actually here we only depends on the divergence between the initial point and the optimizer, but we kind of further relax this term. Okay, so this is everything about the mirror descent, and so go back to that table. Yeah. So in this lecture, we kind of only compared two examples. One is Euclidean, the other is entropy based. But all these examples in this table, they are useful for solving a specific type of problem. Some of them are very useful when solving problems in quantum mechanics, quantum physics. But I don't have time to go over all of them. But basically, if you pick the right geometry, pick the right phi function that has a certain has the right geometry that fits your problem very well, then this mirror descent can converge very fast. Okay. Yeah, and this is a comparison. Well, when we handle the simplex constraint, if we pick Euclidean and negative entropy, there's a huge difference in the dependence of dimension. Okay. So when we do machine learning or other statistics in the with high dimensional data, this will make a big difference. And for this robust regression example, we are only looking at, we are looking at 3,000 dimension, not very big. 20 samples, 3,000 dimension. So there's a huge difference, right? The y-axis is in the log scale. Okay, so and let's see, we have 10 minutes left. So homework 3 is about oh, this is the other course. Sorry, let me go to this one. Yeah, homework 3 is about that classification problem. And homework 4, let's look at this one. Oh, homework 4 is about projected gradient descent. Okay, let's go to homework 5. Yeah, so you can start to look at homework 5. Well, we are solving again, it's the same least mean square problem, but now we have a constraint on the simplex. We're looking for a constraint on simplex. Now, data generation, you can just reuse the problem that you generated in homework 2. And then here we are going to use the mirror descent algorithm with the negative entropy phi function. So phi would be the negative entropy. Now, if you choose that phi and the proper learning rate, then the mirror descent algorithm in one of our slides, it shows that if you choose this phi for the for this simplex constraint, then the mirror descent algorithm simply reduces to the exponential gradient algorithm. So what you do is to implement this exponential gradient algorithm. Well, this denotes the i's coordinate of this vector, right? So this algorithm will updates each coordinate following the right-hand side. Okay, so you don't want to implement this update coordinate by coordinate. That will take a lot of time in the for loop. So you want to do and maybe in MATLAB, write it in a vectorized form and do it in parallel. So this is when you choose the negative entropy as the phi. Now this part, optional part, is simply applying the projective gradient descent algorithm to solve the same problem. And this is the projective gradient descent algorithm. You take a gradient update, you do a projection onto the simplex. Now this gradient is given in homework 2. We know the gradient of this least mean square problem. So the next part, this part, is talking about how once you have a vector, how do you project a vector onto the simplex set? And this is an algorithm to do that projection. Okay. This algorithm describes how you project a point Y onto the simplex set on the high dimension in the high dimensional space. And you have to do it. Well, you have to rearrange the entries in the ascending order and do some complicated steps. But yeah, it's hard to explain what's going on here. But you have to rearrange the entries in ascending order and then do some for loops to get this projection. Okay. Yeah, so if you are interested, you can implement this one, and then you compare these two algorithms, right? One, you have a entropic phi function, and this geometry fits into the simplex set. This is simply a Euclidean geometry because you are just doing projective gradient descent. So you should be able to see a gap between these two algorithms in terms of the convergence rate, convergence speed. Okay. Yeah, I think this is the only simulation for the homework 5. And starting from next time, we will talk about proximal gradient methods. So this one will further generalize the projective gradient method. Okay, so I will stop here today, and I will set up a deadline for homework 4, which is about the projective gradient simulation, and yeah, sometime next week. Okay. Yeah, so please start to work on homework 4 and homework 5. If you have any questions, just let me know. And I will post the grades for these two homeworks very soon. Okay. Thank you, guys. I'll see you next week.
Thank you.